Dear Agronomy 1 students, welcome to Lecture 5 on the topic An Introduction to Soils and Agronomy. For those of you who are listening to this for the first time and do not know me, my name is Dr. Nikki Cooley and I run the subject Agronomy 1. This subject is offered in 2 degrees, the Bachelor of Agriculture and Technology, which is a partnership degree with La Trobe University and Melbourne Polytechnic, and the second degree this subject is offered in is the Bachelor of Equine Studies, a degree offered by Melbourne Polytechnic. Please visit our website at www.melbournepolytechnic.edu.au for further information about these courses and the other courses that we offer. Franklin Roosevelt, who once stated, "The nation that destroys its soils destroys itself." This phrase is very true, and it is now only in the latter stages of the 20th century are we actually beginning to understand the complexity of soil ecosystems and how they play a very important role in agronomy. So in this lecture, we're going to start by introducing you to the soil. What is soil? We're then going to follow by what is important to agronomists and plants. This will be followed by key components and characteristics of the soil. So you'll learn about texture, structure, the important role of pH, and cation exchange capacity. And finally, we will finish with an introduction on soil fertility. So let's start by understanding what exactly is soil. Well, it's a substrate, it's a resource. It is a component of the mineral, organic matter, organisms, pore space, liquids and gases that make up soil. It is formed over time, and the formation of it involves both chemistry and biology. Mostly it can be defined as sedimentary igneous and metamorphic rock structure. That said, there are many definitions of soil. For example, the Soil Glossary, this is from the Soil Society of America, defines soil in several parts. Parts 1, it said it is the unconsolidated mineral or organic material on the immediate surface of the earth that serves as a neutral medium for the growth of land plants. And 2, it is the unconsolidated mineral or organic matter on the surface of the earth that has been subjected to and shows effects of genetic and environmental factors of climate, including water and temperature effects, and macro and microorganisms conditioned by relief, acting as parent material over a period of time. A product soil differs from the material from which it is derived in many physical, chemical, biological and morphological properties and characteristics. That is a very long definition. For the purpose of this subject, I will define soil as in the definition by Schaefer and Monaca in 2009. This definition is in your handout notes. Soil is the biochemically weathered uppermost layer of the Earth's crust. It is a unique ecosystem and an essential resource for the production and growth of plants and crops. For the purpose of this subject, if you do not understand how soil is formed, it is worth stopping this lecture and following the following YouTube link to a lecture on soil formation. This will help you understand and contextualize more how soil came about and therefore how the properties it currently has are important. The lecture is about 16 minutes long and it gives some very good explanations with some good graphics. I've learnt from the slide 3 that the definitions of soil can be quite complex. So let's break it down into ways that we can understand it much simpler. You can separate 5 factors that affect what any soil is like. These are the parent and mineral rock. This predominantly affects the soil chemistry, but also can interact with the physical root growth, for example. The second factors are temperature and water. These are very important not only to the plant but also to the soil configuration. The topography, the diversity of organisms, and the very important component, time. Soils change over the time, they're not static. In order to understand how the soil is made up, we look at what we call soil profiles. These are a vertical section through the soil that extend from the surface to the unweathered rock beneath, and they detail all of the components of the soil. Soil can be divided into layers, or you can think of these as sections, and these layers are called horizons. So, what might a typical soil profile look like? Well, you can see here in the illustrated version that we start at the top with the plants. And just where they intersect with the soil, this is the O horizon. It's about 2 inches thick. It is the top layer of soil composed primarily of organic material, such as litter of leaves and plants, insects and microorganisms. The O horizon is very important in infiltration, that is, water and nutrients getting into the soil. If infiltration characteristics of the soil are poor, then this is not good for your crop production. After your O horizon is that of the A horizon. This is also known as the topsoil. It is where seeds germinate and plants' roots thrive. It is composed of mostly a mixture of sand and silt. Minerals and clay have been removed in a process known as erosion. You do get some organic matter broken down in this horizon or layer. The E horizon, not shown on the figure, is between A and E, and this is the zone where leaching occurs. The B horizon, also known as the subsoil layer, is the layer that contains mineral deposits that have settled down from the upper layers. This is followed by horizon C. This layer is called the regolith and consists of rocks and little organic matter. Even roots don't tend to penetrate this layer. The last horizon, the R horizon, stands for rock, and it refers to the unconsolidated rock or solid bedrock of this layer. Please note this slide was produced by the Institute of Environmental and Sustainable Development and is available on SlideShare. Soil scientists have developed soil classifications that parallel the plant taxonomy. A summary of these soil classifications and where they are located in Australia is presented on the slide. This image was from the journal article by Mackenzie et al. In 2004. You will see that there is quite a range of different soil classifications across Australia. Soil contains organic matter. The amount of organic matter that a soil contains can vary largely. Organic matter is important as it is a source of nutrients for plants. It also has other functions. It aids soil aggregation, it also aids soil structure, and it provides storage for water. So why is soil so important for crop growth and agronomists? Well, soil has many functions for agronomists and crop growth. Principally, it acts as a medium for the production of crops. This medium allows roots to grow in it. This serves two functions. The soil can act as an anchor for the root and also an environment for the root. This environment aids the absorption of water, oxygen and essential nutrients. The ability of a soil to aid water, oxygen and essential nutrients is referred to as the soil fertility. All of these components are required for plant growth and development. Soils also enable a medium for the symbiotic relationships with such organisms such as nitrogen-fixing bacteria. It also aids as a storage of water between rainfall events or irrigation. It is easy when learning about soil and when managing soil to focus only on the physical and the chemical components of the soil. It is easy because we can easily define these and measure them. It is worth noting, though, that the soil is a food web, and a complex one at that. It contains millions and millions of organisms, and they can interact. The organisms include plants, decaying plants, bacteria, fungi, insects, and a whole suite of invertebrates. The soil food web illustration is a summary of some of this complexity and how it can interact. Within the soil's ecosystem, there is a continued cycle between prey and predator. In order for you to fully understand some of the concepts of soil and ecosystems, I'd like you to watch the following YouTube video on soils and ecosystems. This was produced by USDA. When you are watching this video, please ensure that you make notes about the different types of soil organic matter that are described, and about hydrological functions and why they are important in these forests. Essential elements are found in the soil. They are necessary for a plant to complete its growth cycle, whose function cannot be replaced by other elements, and that are compounds of a molecular or enzyme within the plant. Minerals that are derived from rocks in the soil provide many of these elements. In most plant species, there are 17 elements that are essential for plant growth. The compounds such as oxygen, carbon dioxide and water are all obtained from the atmosphere. Plants acquire the other essential elements from the soil. There are several classifications of plant nutrients, but the most commonly used is that based on the content of the nutrient found in the soil. These are separated in either macro or micronutrients. Macronutrients, i.e. compounds that are found in large scales, include nitrogen, phosphorus and potassium. And it is these compounds we often add as fertilizers to the soil to aid our growth and development. You will learn more about this topic in future lectures. Another important concept to understand is that of the carbon and nitrogen ratio and how it relates to decomposition in your soils. The carbon to nitrogen ratio is the relative amount of carbon to nitrogen. It influences the rate of decomposition of animal and plant material in the soil. The C/N ratio varies among plant ecosystems. Therefore, if you add different conditioners such as soil humus or compost, or you leave young alfalfa on your fields, you will have a different carbon to nitrogen ratio, which will significantly influence decomposition. Plants with a low C/N ratio, such as alfalfa, are nitrogen rich and they decay rapidly, while plants that are high in the carbon to nitrogen decay slowly. An example of this is sawdust that has a 400:1 C/N ratio. The reason for the importance of these ratios is that the bacteria and the fungi that decay these plants require nitrogen for growth. If inadequate nitrogen is available, the number of microorganisms will be insufficient to decay the plant material. When carbon to nitrogen ratios are more than 30 to 1, all of the available nitrogen in the soil can be used to sustain existing microbe populations. Therefore, if you add sawdust to your soil, it can result in your crop becoming nitrogen deficient, and additional nitrogen may be required. When considering adding organic material to your soils, whether it be animal or plant waste, manure, hay, etc., be sure to understand and find out what the carbon to nitrogen ratio is and how that will impact on decay, and therefore how it may impact on your crop nutrient requirements and your crop nutrient management. The fractions of organic matter have many roles. These roles include sequestration of nutrients, that is, such as carbon. As carbon is a major component of the organic matter is therefore an important component of the global carbon cycle. Organic matter is a source of nutrients. It acts as both a reserve for the essential nitrogen, phosphorus and boron, but also nutrients are attracted to the surface of organic matter. Nutrients may be a component of the organic matter too. Organic matter is a binding agent that joins the mineral proportions of the soil together. The aggregation of soil particles is important for the soil tilth and aeration. These are important for successful plant growth and development. Organic matter absorbs water like a sponge and it retains it for plant growth. And finally, organic matter can tie up toxic chemicals and pesticides that would otherwise contaminate the groundwater. This is referred to as chemical sequestration. In the organic matter fraction live the humble earthworms. A good population of earthworms indicates a healthy soil. Earthworms are small animals that can improve the soil structure by contributing to physical breakup of the soil. Some soils can contain up to 300 earthworms per metre cubed. There are 7,000 species of earthworm. Across these species there are 3 classifications: the litter dwellers, the shallow soil dwellers, and the deep burrowers. They play several critical roles in good agronomical soils. They shed crop residues and initiate decomposition of the organic matter by bacterial and fungi that feed on the organic matter. Their extria is in turn consumed by the soil organisms. They mix soil and organic matter, and they bury soil organic matter. They allow tunnelling to occur within the soil profile. This adds aeration and provides pathways of movement for water and plant roots. Let us now look at the soil properties that affect plant growth and crop growth: texture, structure, and chemistry of the soil. That is, such things as pH and cation exchange. Soil texture defines the soil fineness or coarseness. A soil can be very fine or very coarse, or somewhere in between. It is determined by the type and the amount of specific soil particles. These are soil, silt and clay. Sand and silt are principally silica, while clay, being the smallest compound, is comprised of a mix of compounds which include silica, aluminium, oxygen, hydrogen, potassium, magnesium and phosphorus. It is a chemically reactive particle and provides most nutrients for plant growth. Agricultural soils tend to be a mix of sand, silt and clay. Principally, the soil is composed from sand, silt and clay. Once you know the composition or the percent of each of these components, sand, silt and clay, you can then use this information by using a soil triangle, the figure on the slide, and this you can then identify what soil type you have. For example, a soil with a high clay content, low sand and low silt is described as clay. However, a soil with an equal amount of clay, silt and sand is called a clay loam. Soil structure describes the clustering of soil particles into various shapes. Productive agricultural soils often have a granular structure in which clusters of soil particles are bound together by organic matter and clay. Well aggregated granular soils have good aeration and tilth. Tilth refers to the soil having beneficial qualities related to crop growth. Soil structure can be defined by the volume and the arrangement of these pores in the soil. This determines concepts such as soil-water movement and airflow in the profile. This affects soil friability, that is, the ease of rain infiltration and rain runoff, cultivation and growing crops. Damaging soil structure can be an issue that you'd like to avoid. Livestock can pulverize the soil, that is, they can result in the destruction of large and small soil channels. These channels allow the rapid air and water infiltration. Wet soils often result in compaction and breakdown of soil aggregates if livestock are run on them during this period. Binding organic matter is very good at binding and breaking up the soil structure. Soil structure erosion, low organic matter, causes collapses in wet soil conditions, reduction and infiltration and increase in runoff. 5 to 10 times more erosion when poor soil structure exists. There are a number of clues that can lead you to identification of poor soil structure. Look in areas that you suspect you may have a problem and compare them with a similar soil that you suspect has good structure. For example, before livestock were grazing. Rill and sheet erosion is where water runs over the soil surface, strips away thin sheets of soil, only millimeters at a time. When the water collects, small eroded channels form down the slope. This is rill erosion. Surface crusts reduce infiltration to water and restrict seedling emergence when they become dry. Cloddiness. After a single cultivation, brick-like clods are formed. Further cultivation is required to produce a suitable seedbed. Some plants can be used as an indicator of bad pore structure. One such plant is the toad rush. It grows where water has ponded on the surface. Ponding is where water after a light rainfall accumulates. It does not soak into the soil. A hard surface may be seen with poor soil structure. This is when the soil is dry and tests the hardness. The depth of penetration of failing mattock or with a pick can be used to test this. Compare different soils. Poor infiltration may result after the first rains, after a dry spell. Water does not infiltrate into the soil very far. And finally, the presence of organic matter. Soils tend to be brighter and paler in colour when they do not have much organic matter. When there is a large concentration of organic matter, the soils tend to be dark. So what course of action can you take if you suspect or find poor soil structure? You can change your management to a permanent pasture. Plants will protect the soil from erosion, and the deep roots from the pasture will help the pores and channels needed to improve infiltration, and plants will naturally increase the soil organic matter. Manage the pasture well, however. Ensure that you use water, nutrients, and light grazing wherever possible. The application of the compound gypsum can be used to improve your structure. If you apply gypsum, it is best to tackle slacking and dispersion of your soils. The rate of gypsum that tends to be recommended is 2.5 tonnes per hectare. Gypsum works by supplying calcium, which disposes the sodium from the clay surface. It is advisable to test for your exchange cation levels, and this can indicate your application rate. We will also look at soil chemistry. Soils have many chemical properties that are important for plant crop growth and development. The three that we're going to concentrate in this lecture are cation exchange capacity, pH, and salinity. Small crystalline clay particles and organic matter that exist in the soil are chemically active and usually have a negative charge. The negatively charged surface of these particles enables them to attract positively charged particles. If you are able to link to the following website, you will see a demonstration of the chain exchanges of these charges. These images are on a conceptual nature. The amount of exchangeable cation a soil can sustain is called the cation exchange capacity. Where this is relevant for you as an agronomist is that the higher this cation exchange capacity is, the more able the soil is to hold nutrients and is therefore fertile. The cation exchange capacity for the soil particles clay is 30 milliequivalents per 100 grams, for sand it is 9 milliequivalents per 100 gram, and humus has a high level of 200 milliequivalents per 100 grams. From these three components, this shows you that adding humus to the soil will increase your cation exchange capacity. There is a range of exchangeable cations found in the soil, and some are listed on the slide. Their ability to attract varies also. That is, aluminium is very attracted or strongly associated with the soil, whereas sodium is less so. Knowledge of your cation exchange capacity in your soils will enable you to manage your soil environment correctly. This is particularly important if you are going to add supplements to the soil, and it is also important in your nutrient management of your soils. Acidity is the chemical condition of the soil and is measured by the pH scale. The pH scale starts at 1. This low number represents a strongly acidic environment, and it ends at 12. The high number of 12 represents a strongly alkaline environment. Acidic soils have a pH of 4.5 or below. This is when the pH is measured in the soil solute calcium chloride. Soil pH can also be measured in water, and you need to be mindful of how it is measured in the interpretation of that pH. Acidity and understanding your acidity is important because it can reduce yields and also interfere with nutrient availability and nutrient uptake. Australian soils have a tendency to be slightly acidic or acidic. There are several consequences of acidic soils. It can prevent legumes from nodulating. It results in a reduction of recycling of your nutrients by beneficial soil microorganisms. It can increase toxicity to your plants by two methods. One is the release of aluminium from the soil, and two is the release of high magnesium levels. High magnesium levels are typically seen in hot, dry, poorly drained acidic soils. If you have low pH, you can have a decline in nutrient availability. Available aluminium and iron may tie up valuable phosphorus, for example, or it can cause molybdenum deficiency. There are a range of effects of acidic soils. Different crop and pastures are affected differently by different aspects of soil salinity. Soil salinity can affect the top 10 centimeters, and it tends to be where you see the problem. However, the problem may occur at the subsoil level as well. Subsoil acidity is costly and very difficult to adjust for. The diagram on your slide describes the influence of pH on soil fertility and nutrient availability. If you start by looking at this figure at the pH 7, which is regarded as optimal, you will see after studying this slide that all of the nutrients can be taken up. If, however, your pH is above 7, it is regarded as alkaline. Alkaline toxicity can occur. The more alkaline the soil, the more toxicity results. If you have alkaline soils, you can get deficiencies of iron, manganese, zinc, copper and boron. You will tend to see an excess of sodium, which can be toxic to the plants. If you reduce your pH and you are entering acidic soils, as your pH reduces, your toxicity increases. If you have acidic soils, you can have deficiencies in magnesium, calcium, potassium, phosphorus and molybdenum. You may also see an excess of aluminium, manganese and iron. This demonstrates the importance of agronomists to understand your soils. Add your nutrients to your crop. You could at worst be wasting your time if you get your nutrient-soil interactions incorrectly. You could also result in a significant loss of yield, nutrient deficiency, and toxicity issues to your plants. So what are the signs of soils that are acidic? You tend to get uneven pasture or crop growth. Pay attention to acid-sensitive plants, and you may see the invasion of weeds that are acid tolerant. Acidity across a field tends to vary significantly. This may match your uneven pasture variation. You may see poor nodulation of legumes. Stunted root growth and increase in root disease may also occur. If you find that you are having difficulty in certain crops, such as lucerne and medics, this may suggest soil acidity problems. And finally, you may see the formation of organic mats on the soil surface as a result of the loss of biological activity. So what is the action that you should undertake? Well, if you suspect soil pH issues, the first thing to do is to conduct soil pH tests and aluminium level tests. Remember that soil acidity varies greatly due to rain and temperature over the season. So when you are conducting your soil samples, not only should you take a close note of the climate and conditions when you take the samples, but also that you can compare these conditions at similar times. Ensure that you understand the difference between measuring pH in water versus measuring pH in calcium chloride. It is often thought that the measurement of pH in calcium chloride is more accurate. and more meaningful for agronomists. 20 or more samples should be collected from a paddock due to the large variations seen in acidity. There are a number of actions that you can take if you suspect acidic soils. The most common is the addition of lime. A heavy application may be as high as 6 tons per hectare if you have a seriously acidic problem. The lime needs to be spread evenly over the affected areas and ideally incorporated into the soil. This is where managing subsoil acidity can become very tricky. The lime works by changing the pH and neutralizing the surface. As a rule of thumb, the guide of lime to add is 2 tons per hectare for every 1 pH change you wish to undertake. Ensure that you measure your pH after your lime application. The lime application may depend on the soil type, as clay-loam soils tend to need more application than sand soils. It is best that you add your lime at 1 ton per hectare every 8 weeks following the initial application. Continue this for the rest of the season. You can also look at the method developed by G. Fenton in 1993 about strip application of lime. This is where a strip of lime is applied on the field, and you monitor the performance of the plants over time to see if this lime has made meaningful differences in your plant growth and development. Another action that you can consider is to do nothing. This is not advisable, however, because plant yields will continue to decline even if you do not see this initially. Another action could be considered is to grow more tolerant species. If you do this alone without trying to adjust for the pH, this is probably only a short-term fix, as your pH or your soils will become more acidic. And finally, the fourth action that you can consider is to change your farming system. If you reduce the intensity of your cropping, for example, and you lightly graze your paddocks, you may increase your acidity. There's been experiments where lightly grazed undeveloped pasture in acidic soils only needs rates of lime application as little as 0.5 tons per hectare every 10 years. Intensive production systems of high crop yields, such as hay cutting areas and productive pastures, need about 3 tons per hectare every 10 years. You should also consider better nitrogen management, better soil moisture management, and an increase where possible of perennial pastures and deep-rooted plants if you have acidic problems. Soil salinity is also called saline sodic and saline sodic, and these terms are used interchangeably. Salinity occurs due to the accumulation of salts such as sodium, calcium and magnesium that dissolve in water. As the water table moves, so does the salts. These salts form a chemical reaction between acid and a base. Most soil salts are sulfurs, SO4, and the chlorides, Cl2. Salinity tends to be associated in hot, dry environments due to the higher evaporation of water from the soil's surface. There are 2 types of salinity, dryland and irrigation. Salinity reduces yields because salts cause plant dehydration. So there are several causes of salinity. These can be as simple as land clearing, or some traditional farming practices using clover and pasture can result in high salinity levels. How you manage the water is usually the most common form of salinity. If you raise the water table, you can release salts which can then unlock the problem to other areas. Salts are drawn down by what we call capillary action to the surface. The image on the slide was taken from the Mallee region in Australia by the Department of Primary Industries. It illustrates the effects of salinity. It is toxic to plants. Salinity may cause waterlogging issues. When water is in the soil, it is not used. Deep drainage to the water table increases. Native trees have been found to be very effective at using this wastewater, and removing them reduces the capacity and leads to salinity issues. Annual crops and pastures tend to be shallow-rooted in nature, and they do not use deep water, this also leading to salinity. Overgrazing can reduce leaf area and lowers plant water use. Sowing late can also cause or make salinity problems worse, as if the paddock is not using the water in the autumn, this can again add to the problem. Disease and inadequate fertilizer, or any factor that limits plant growth, can also impact on salinity. Where you allow long fallow, you aim to store water, and often the soil is full before the crop is sown. Additional rain recharges the groundwater, adding to your salinity problems. Leaking dams are an obvious one, but little thought about. And finally, poor surface drainage. Water laying on the land powers plant growth and water use. This then leaks into the water table if it's not used up. So what can you do if you suspect salinity problems? Well, the first thing to note, it tends to be a whole farm or catchment approach. A farm plan is highly recommended, and the Department of Primary Industries can assist you with such a plan. Ideally, you aim to use water more efficiently. You can do this by planting native trees and shrubs, changing your cropping practices to perennial pastures that are well managed. High water use cropping, early sowing varieties, and avoid disease of these varieties. You need to consider good crop rotations and allow a longer pasture phase by using perennials and avoid long fallows. Surface drainage should be repaired, and use groundwater irrigation for stock, for example. I'd like to bring this lecture to a close by looking at erosion and conservation of your soils. Erosion is the accelerated loss of soil through the action of wind or water. Management techniques such as conservation tillage and growing permanent vegetation to cover your soil can minimize this erosion. A useful tool in conserving soils and preventing erosion is being able to estimate ground cover and then manage accordingly. Note that ground cover does not include bare or loose soil, or clay pans or scales. However, ground cover does include live plants, sticks and logs, litter and dead plant material, rocks and stones, dung, soil crusts able to withstand a hoof impact, and plants such as lichens. This slide shows two images obtained from DPI. One on the left-hand side demonstrates 20% ground cover estimation, while the one on the right-hand side shows 80%. To avoid soil erosion, you should aim for a 70% or more cover on your soils. Let us review what we have learnt in this lecture. Well, we've understood that soils play a role in the commercial growing of plants, that this role is actually quite complicated, that this role involves us understanding about something called soil structure, soil texture, and soil chemical properties. We've importantly understood that the soil just isn't physical matter, that it's actually huge biological components. That is, there is ecosystems that are made up of millions and millions of components that can either aid crop growth or they can stunt it or reduce it, depending on the complex roles. It is my belief that science is just beginning to understand the complexity of soils, and that over the next 5 to 20 years, with our new technologies, we will begin to have a better understanding. In future years, you may concentrate more on the managing of your soils than the actual managing of your crops, but that's still up for some debate. We've also presented some information that links erosion and ground cover and how this is also important in soils and how you should manage this in an ideal situation. Thank you very much for listening to this lecture. This brings us to the end of an introductions of soils and agronomy.